In lesson 2.6, we have two objectives. One is to solve polynomial inequalities, and the other is to solve rational inequalities. So in both objectives, we're solving inequalities rather than equations. So we're going to be looking at where our curves are below or above the x-axis, basically. And our polynomial functions are smooth, continuous curves. That makes them a lot easier to deal with. We're simply looking at where our curve is above and below our x-intercepts. Now, the x-intercepts are the zeros of our function, which we've been working so diligently on finding. So we're going to use the concepts of finding zeros of the function along with our graphs to help us figure out where it's above or below, or we're also going to integrate some ideas of the interval line test and also end behavior. We'll go right into a couple of examples here and try to keep it fairly short and sweet. Both of these are relatively simple examples. They're both quadratic, so we're going to start with the first one. In order to solve a quadratic, whether equation or inequality, you want to get one side equal to 0, so x squared plus 5x. I want to move the 20 over, so it's going to be minus 14x. 14 is less than 0. We can use strategies of either factoring or a quadratic formula. This one does factor fairly easily. So it factors into x times x. Signs have to be positive and negative. Factors of 14 that are 5 apart are 7 and 2. Which leads us to the fact that our related zeros, if these are our factors, our related zeros are a negative 7 and a positive 2. Now last year we did several of these, and even the year prior to you've done some of these. But what we're going to do is we're going to place our zeros on the x-axis. And just to make this relatively a simple sketch, I know the graph crosses the x-axis, and this really represents our x at a negative 7 and a positive 2. Because of the nature of the graph, I can look at the x squared and I know it's a smiling curve, so I know it's going to be smiling going through at negative 7 and going through at a positive 2. At a negative 7, our exact answer is 0, and at a positive 2, our exact answer is 0. All we got to do now is interpret our inequality sign, which says we want values that are less than 0. According to my graph, the parabola is less than 0 when it's below. These are locations where it is equal to 0. I don't want to equal 0, I want to be less than 0, and that's the location where our graph is below. So what are the x values that represent the y values that are below? Everything between a negative 7 and 2. So in our solution set, what we're going to do is going to use some interval notation. We want a parenthesis from a negative 7 to 2 parentheses. That shows all the solutions from a negative 7 to 2. Every x value in this range will tell us an output that will be less than 0. So we've just solved the first one. That's the idea and the concept behind it. They are going to introduce another little technique in here. It's called an interval line test. As soon as I put on a negative 7 and a positive 2, it divides your x-axis or your x number line into 3 intervals. There's an interval here that goes from negative 7 to negative infinity. There's an interval on the inside, I'll call it interval 2, which goes from a negative 7 to 2. And there's a third interval, which is from a positive 2 all the way to positive infinity. The interval line test says simply take any value that goes from one of these intervals. So I could take a number like a negative 8 and do a sign analysis test. So we did this in the previous one. For sign analysis, all I do is I want to know if it's positive or negative. So I'm going to show you in some simple examples. You don't need to do it on this, but this general scheme or strategy works for all polynomials. So even if it's a cubic or a fourth degree polynomial and so on. So if I put in a negative 8, this factor here will be negative. If I put a negative 8 there, that factor will be negative. And negative times negative is a positive. So we have positive results. When we are looking for less than or equal to 0, we're looking for negative results. So if this is positive, our answers are not in interval 1. If you pick any number in interval 2, I'm going to choose 0. It's the easiest one. That'll give me a positive value for this factor. It'll give me a negative value for that factor. And positive times negative is negative, which is exactly what we want. And that's what we knew our solution was. And then you can pick a number out here larger than 2, such as 3. And that'll give us a positive and a positive. Multiplying two positives together give us a positive. We're looking for negative. So the interval line test will be more valuable when you get into larger polynomial functions such as cubic and quartic. I showed it to you here on this quadratic just to show you the general strategy. It's called the interval line test. In 1b, there's only a squared term in it, so again it's going to be quadratic. In order to solve a quadratic, you got to get one side equal to 0. So I'm first going to expand the x minus 4 squared, so that's x squared minus 8x plus 16 is greater than 4. We're going to require us to move the 4 over, so x squared minus 8x. We're going to subtract 4 from the 16, gives us positive 12 is greater than 0. This one will factor again, it looks like. So we'll go x and x. The factors of 12, that'll give us an 8. If we go minus 6 and minus 2. So we know now from our factors what the zeros of the function are. We should cross the x-axis at a positive 2 and a positive 6, which tells us where it's exactly 0. So this is where it's exactly 0. I don't want it to be exactly equal to 0. I'm going to put open circles on those because we want to be greater than 0. Again, because it was an x squared that was positive, I know the graph is smiling. So I can use more or less an end behavior analysis. I know on the end behavior of our polynomial function as x approaches a negative infinity, y's are going to be approaching a positive infinity, and that's the values that we want. We want the positive values. Again, we can get that probably just directly from our graph without using the end behavior. We just know that the part of the graph that is above 0 is to the outside of a positive 2, so less than a negative 2, and greater than 6 to the outside of 6. So we're going to write our solutions in interval notation. We're going to go from negative infinity to a positive 2. We're going to union that with parentheses, because we don't want to include the 6 to infinity. So those are two fairly simple quadratic examples of polynomial functions, and we're solving those inequalities. The next few examples will be a little bit different. They're going to throw in some different strategies, but let's stop the recording and start those.